Okay, so today is the day we do mean value theorem. This is the third of our existence theorems. Number 3, number 2 was EVT, and number 1 was IVT. Okay, so with these, we always said, okay, IVT or EVT guarantees blah, 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 blah. So same thing with MVT. Okay, it guarantees that there is at least one point C, some x value, at which the slope of your tangent line equals the slope of your secant line, or whatever's being asked from a particular problem. And the only way this is guaranteed is if our function is continuous on the closed interval, as well as our function is differentiable on the open interval, the interior values from A to B. So please, and make sure you get these notes because they're super important, and now you're going to need a diagram. So that this makes a little bit more sense as to what we're looking for. Okay, now these obviously would be calculations, and these two numbers are supposed to be equal. Okay, and here's why. So let's draw out my function, not erase it. Let me try again. Okay, I'm not doing very well. Let me pause this and keep trying. Okay, better. So here's f. It's on a closed interval from A to B. Okay, or it could be any other values from A to B. So our function could be some continuous function, but we're only looking on from A to B. And what MVT guarantees is that there is some slope, okay, of our tangent line that will equal the slope of this secant line that I just drew. So that's the slope of my secant line here. And it could be in more than one place, okay, so that's why it says at least one point C. But to my diagram, I'm just basically going to have this one value of C, that the slope would be the same. Okay, the slope of my secant line and the slope of my tangent line. Okay, so slope of the tangent line when x is equal to C is supposed to be drawn the same slope as the slope of my secant line from when x equals A to when x equals B. All right, and that's MVT. All right, so there's one more thing that I'm just pull up as you're copying this down. I'm going to read this to you. Okay, and this is a good note. So MVT connects the average rate of change. If you remember when we went over average rate of change or average velocity, I always said it was the difference quotient, and that's this right here. It's the slope of your secant line. It connects that over an interval with the instantaneous rate of change, and that is also instantaneous velocity or rate of change or velocity when you take the first derivative. Okay, of a function at a point in an interval. It makes that connection. So it's a really cool theorem. Okay, so we're going to do two examples. Okay, example 1, show that the function f satisfies the hypotheses of the mean value theorem on the interval from 0 to 2 inclusively. Then find a solution C, C is like our x value, to the equation on this interval. Okay, so here we go. Pause the video to write down your example problem and then play the video so that you can get done the work so you have problem work and answer to study with. Don't just watch the videos, you have to do them. So here we go. In example 1, since it's saying show that the function, there's like a certain procedure. And I'm going to say it's really just statements. So f of x is continuous on the closed interval from 0 to 2. And f of x is differentiable, I'm going to abbreviate, on the open interval from 0 to 2. Therefore, MVT applies. Okay, that's actually all you need to do, is just have this statement. Okay, so now we're going to work on the second part here. All right, so what we want to do is two things. Okay, we want to take the derivative of f of x. We want to take the slope of the secant line from when x equals a to x equals b. And then we're going to set them equal to each other. So here we go. So the derivative here is 2x, and the slope of our secant line would be 2 squared minus 0 squared over 2 minus 0. Now we're going to set them equal to each other. So when we simplify, we end up where x, I'm doing this baby steps, I don't know why. So when x is equal to 1, that's our c value, because x is equal to c. You can actually just circle this, or you can say c is equal to 1. So we found the solution c to the equation on this interval. Okay? So now, if you're not understanding how that ties into our graph, or you want to understand what it is that from 0 to 2, okay, we know what this would look like from 0 to 2. Okay. We have this function, and we have a secant line from 0 to 2. We want to know where the slope is the same, and it's actually when x is equal to 1 that the slope is the same. I try to draw it in there very well. So they're going the same direction, same slope, and that's it. So we found that value of c. Let's move on to example 2. Again, you can always rewind the video if you didn't get the problem work and answer. But, well, the problems are still here. So get down example 2, and then we're going to start it. Okay, so we have a different function. You should identify the function. It's a positive square root, difference between perfect squares, number, variable. So this is a semicircle above the x-axis. And we have the points A and B. Find a tangent to f in the interval from -1 to 1 that is parallel to our secant A to B. So in example 2, okay, this is a little bit different, because in example 2, MVT doesn't apply, but we can still go through the procedure, so there's no guarantee. But that doesn't mean that there isn't an x value where the slope is the same. It's just that MVT can't guarantee that. Least one solution. So similar to IVT, where we had to say that there was at least one solution, here that there's at least one, I should say x value, not solution, at least one x, or c, such that the slopes are the same. So in example 2, we just have to go through a procedure and see if it does work out, okay? So actually, in exploring this function, it is continuous even though it's on an open interval, okay? So we're going to take the first derivative, for f of x. And if you need to rewrite f of x, please do. So it's the quantity of 1 minus x squared to the 1/2 power. So I did power chain rule here. And we're going to do the slope for the secant, okay? And the slope of the secant is f of 1 minus f of negative 1. So we're plugging 1 into our function, and we're plugging negative 1 into our function, subtracting them. So now if you know this is a semicircle, you know that connecting point A to point B, and we're looking at our secant, what that would look like. It would actually be a slope of 0. So just double check you're not dividing by 0 here. So we want the slope here to be 0. Okay, so that the tangent is parallel to secant AB. If it's parallel, it has the same slope. So let me simplify this expression on the left-hand side of my equation a little bit more so that we can easily work with it. So in this case, we find that x is equal to 0, which kind of makes sense if you know its graph. If not, that's okay. That's actually why we have this procedure. So at x equals 0, the slopes would be the same. And we need the tangent. When they implied that you need tangent, you need the tangent line. So if it's a line that has 0 slope, it's always the y equals b equation. B in this case is going to be 1. And the reason for that, we can solve for when x is 0. If we just plug 0 into our function, we get the answer of 1. And so example 2, we found the tangent line to f on our open interval that is parallel to secant AB. All right, so those are two different types of questions, but both of them needing the concepts of the MVT. And I'm going to give you some problems to work on, so good luck.